for attending this session, which will be about renewable energy industries. So I am Emmanuel Remy. I work for the R&D division of EDF, Électricité de France, which is the French and the world leader in electricity utility. So this morning, I'm very honored to chair this session, and I'm very pleased to be here in Angers this week. And we will start by Olivian Savin, who will talk about the influence of starts and stops on the aging of hydroelectric generator stages by thermal cycling. And he will present to us an empirical study and then an accelerated lifetime model. So, Olivian, maybe you can come here and take the mic. Do you have your presentation?
So, thank you, everybody. Today I will present a paper on the influence of start and stop on the aging of hydroelectric generators. This work was done in a collaboration between the EDF, so Electricity of France, and the University and the Polytechnic Institute from Grenoble. We will discuss about the context in the beginning, then a few words of the state of the art. We will describe our methods that we use. We use two methods. Then we will see the results, and of course, in the end, we will have the conclusion with achievement, limitation, and perspectives. So the industrial context, why we study the effect of cycling. Due to the regulation in the early 19th in Europe of the energy market, the hydropower equipment started to have an increased number of start and stop, because the renewable energy, they had to be integrated on the electrical network. So the operators need to adapt to the new operation constraints. This might lead to reduce of lifetime of the equipment, and of course, in the end, of additional costs that needs to be evaluated. The research context. So we know we start from the beginning with the increased start and stop, and we know there is a deterioration. We identify the deterioration as a thermal cycling, and we know it's on the insulation. In the end, we will have a decreased lifetime, and we have to evaluate the cost. So in the figure above, we can see the research context, and of course, all of that, like the evaluate of the effect of start and stop and deterioration, are part of our context. A few words about the contribution. We evaluate the effect of start and stop. First of all, we analyze all the subcomponents of generators, and then we identify the degradation phenomena. So the first step that we made, and then we propose two studies to estimate the decreasing in lifetimes. So we have two types of categories, and we use the rewinding experience with the right censorship. We try to model it after with an accelerated lifetime, and we do two types of simulation. So briefly, the two methods of reliability law. So we use real data rewinding years, and we use also a right censorship. We will discuss after exactly what right censorship means. And then we estimate the lifetime of two types of hydropower plants. We call it cycled and non-cycled hydropower plants. So once we will see the effect of the start and stop, then we try to model it, and we model it with real monitoring temperature data. We simulate some thermal cycles, and in the end, we will estimate an accelerated factor. In the next slides, I will explain exactly the two types of methods. So in the beginning, we done a study on almost 300 EDF generators in the past 30 years, and we saw that the main defaults are related to stator insulation. The half of them are related to stator insulation. There's also defaults related to rotor insulation and other type of defaults. We call this a team degradation, meaning thermal, electric, ambient, and mechanic. For the stator insulation, the thermal degradation is the most important one, and we try to model it. So with the first method, we use a Weibull reliability law with two parameters, alpha and beta, and we do two types of groups. The first group, it's called low cycle plants, where we have runoff rivers, and they are like they have an average number of one cycle or less than one cycle per day. And the second group, we have the high cycle plants that have an average number of 2 or more cycles per day. So this is the average on the whole life. It's not the average every day that they do. Sometimes the high cycle plants do more than 2 cycles per day. So we see we have almost 300 generators that they are low cycled, and almost 43 high cycled plants. Why we use a right censorship? Because they are generators that they are still functioning now. So there are hydropower plants that the commissioning was in the early 20th century. So they have more than 100 years. Some of them they were replaced, some of them they are still functioning. So we use a right censorship to model it. The results. For the first category with the low cycle power plants, we estimate a lifetime of almost 60 years. And for the second group, we estimate a lifetime of almost 50 years. So the difference in lifetime comes mostly from the operating mode of plant, and more particularly for the second group, from the operation at an intensified start and stop frequency mode, which have an impact on the wear and tear of the equipment. So in the first graphic we have 60 years, and the second graphic we have 50 years. So there's a difference of almost 10 years between these two groups, cycled and non-cycled plants. This for us, it means that there is the start and stop has an effect on the lifetime of generators. So once we saw this effect, we try to model it, and we model it with an accelerated lifetime model. It's called Coffin Manson model. That basically we have the lifetime, and the lifetime is divided by this accelerated factor that it's estimated, and we have the average temperature, the amplitude, and the cycling frequency. So in accelerated lifetime models, we have something that it's used like T0, delta T0 and F1. We call it basic level, so it's for one cycle per day. And we have the accelerated cycles like T1, delta T1, and F1 for the accelerated cycles, meaning 2, 3, 4, and so forth, cycles per day. On the right side of the slide, we have a real temperature evolution with regarding the power evolution. So we see the thermal cycling and the power, the start and stop that the hydropower plant are doing. We studied pump storage power plant because they're functioning all or nothing, meaning when they start, they go to the nominal power, and when they stop, they go to the zero power. We can see the cycles, they are very different, and because of that, we try to model it and to try to make it more easy for us to study. And we took a normal cycle, so a base cycle, we call it, one cycle per day, and we made a decomposition in 5 polynomial equation. So we see the 5 stages of a cycle, A, B, C, D, and E, with the starting to work, and then have a constant temperature, and then starting to descend for the cooling part of the generator. So we simulated 2 types of cycles depending on the strategy that it used. The first strategy, we simulated pump temperature cycles with operating time equal to cooling time. What does that mean? We have a cycle per day, and in 24 hours. So 12 hours, it's the time of functioning, and the rest of it, the other 12 hours, is the cooling time. So we've done up to 7 cycles we simulate up to 7 cycles per day here. And we saw that the average temperature doesn't change a lot. So we have between 72 and 75. The amplitude it's between 20 and 30, and as I said, the cycles between 2 and 7. On the other side, we have simulated pump temperature cycles with fixed operating time and a cooling time that decreases with cycle. What does that mean? That we have a cycle per day, and we know that it will function, the generator will function for 3 hours and a half, and then we simulate up to 5 cycles per day. So we saw that if the generator works with a fixed time and that is bigger than the cooling time, the average temperature goes from 60 to 80, meaning that there's a high influence of the average temperature. The amplitude is the same like in the first simulation, and the cycles that they are up to 5 per day. So these are the two types of simulation. We see the difference between the average temperature, the amplitude is the same, and the frequency up to 5, it's the same. And what we observe on the acceleration factor, we saw that for the first simulation, so when the cycles are the time of functioning, it's equal to the cooling time. For 7 cycles per day, we can reduce up to 20% the lifetime of a generator. On the other side, on the second simulation, if we do 5 cycles per day, where we saw that the average temperature has a big influence on it, the reduced lifetime can be up to 75. So it's a big difference between the two simulations, meaning there's a difference between the two types of strategy that it's used. Some conclusion that we saw the lifetime decrease with increasing cycles, because an accelerated factor, if the value is less than 1, the lifetime will increase. If the value of acceleration factor is greater than 1, it means it will decrease. So we saw in both cases that lifetime is decreasing. So this is a predictive model and shows how it could capture the effect of different cycle modes on lifetime, then rather than fitting the real data to estimate a lifetime reduction on a cycle. And as I say, depending on the strategy used, we have different values for the reduced lifetime, and this is mainly due to the average temperature. So in conclusion, what are the achievements? We saw that the thermal deterioration due to start and stop on stator, it's very important, and it's the main cause of deterioration. The power plants with more cycles per day have lower life expectation. We saw from both simulation and for the first method that we use. And depending on the strategy, we have different values of lifetime. What are the limitations and perspectives? We had little scientific information on the wear and tear of generator related to start and stop. This is important because the deterioration was studied, but related to start and stop wasn't studied until now. Data availability of the rewinding gears. So we have the history data for more than 100 years, but the quality of the data is also very important. So we also had a focus on that point. In function of different strategies, we can influence the lifetime of a generator. And I've studied only the pump functioning mode. So the pump storage power plant, they also have turbine mode, and this needs to be studied as a perspective. So thank you for your attention, and if you have a question, I'm glad to answer it.